Assalamu alaikum. Today we want to continue talking about chapter 2, section 2.4 titration curves. Now in aqueous solution, the relative concentrations of a weak acid and its conjugate base can be related to the titration curve of an acid. So titration is an experiment in which measured amounts of a standard base are added to an unknown concentration of an acid. And titration begins by using a pH meter until we reach something called the equivalence point, the point in titration at which enough base has been added to neutralize the acid. So this is called the equivalence point. Now if we look at this figure 213, titration curve for acetic acid, we see here, we start here titration at low pH. At the beginning we measure the pH before adding any base, then we start adding a base. As we add the base, then the pH increases now until we reach this point. This point is called midway titration, where both the acid and its conjugate base exist in 50-50 ratio. Then after that, we continue adding the base, and the pH continues to increase until the titration ends. This is called the end point or equivalence point, and in most cases these 2 points are coincide, the equivalence point and the end point. Now as we saw in our discussion of the Henderson-Hasselbalch equation, the pH value equal to the pKa corresponds to a mixture with equal concentrations of the weak acid and its conjugate base. So in this case both acetic acid and acetate ion exist, and the pH at the inflection point is equal to the pK of the acid, as we can see here. So at this midway titration, this is called the inflection point also. Now since the concentration of the acid and its conjugate base are equal, then pH equal pKa of the weak acid. Now we can titrate NaOH with acetic acid by using 1 mole of the base NaOH. This is we saw previously, but also we can here titrate 1 mole of acetic acid with not 1 mole of the base, but rather by 0.1 mole of the base, 0.3, 0.5. So here we want to use the Henderson-Hasselbalch equation to calculate the new values of pH at these points. Now we can approach this problem as an exercise in stoichiometry. If you look at the equation, the ratio is 1:1 moles of acid and base. Now the difference between the original number of moles of acid and the number reacted is the number of moles of acid remaining. So acid is in excess and all the base is reacted or titrated. These are the values to be used in the numerator and denominator respectively of the Henderson-Hasselbalch equation. Now we'll begin with the first case. When 0.1 mole of NaOH is added, then it will consume 0.1 mole of the acetic acid to form 0.1 mole of the acetate ion and leaving 0.9 mole of acetic acid. So we can say the composition is 90% acetic acid and 10% acetate ion, and we can apply to this equation to calculate the new pH. As it is expected, the pH starts to increase as we are adding the base. Now, similarly, we can Calculate the new pH after the addition of 0.3 mole of NaOH. In the same way, now the composition is 70% acetic acid and 30% acetate ion, and again the pH is 4.39, increased. Now, however, when we added 0.5 mole of NaOH is added, then 0.5 mole of acetic acid reacts to form 0.5 mole of acetate ion and leaving 0.5 mole of acetic acid. Now the composition is 50% acetic acid and 50% acetate ion. And now we apply to the equation and we get the value of pH equal 4.76. The pH also increases. Now note that this one is possible without doing much math. We know that when H concentration of HA equal concentration of A minus, then the pH equal pKa. Therefore, the minute we saw that we added 0.5 mole of NaOH to 1 mole of acetic acid, we knew that we had added enough NaOH to convert half of the acid to the conjugate base form. Thus, the pH has to be equal to pKa. Now, dissociation constants for 3 groups of acids. Now, acids can be classified as being monoprotic. They release 1 proton and have a single Ka and single pKa. Diprotic, releasing 2 proton ions and have 2 Ka and 2 pKa values. Or polyprotic acid release more than 2 proton ions and have more than 2 pKa values. Now, when the pH of a solution is greater than the pKa, here, then the conjugate base predominates and proton is off and the substance is deprotonated. When the pH is less than pKa, then the weak acid predominates and proton is on, the substance is protonated. And we can understand this more if we go back to this titration curve. Now, at a pH value lower than the pKa, then proton is on. When the pH is greater than Ka, then proton is off. So at the beginning here, proton is on, which means the acid is protonated, and at the end we have proton off, the acid is deprotonated, and in the middle it's half protonated. Continuing, to summarize this session, we can say in the region of the titration curve in which the pH changes very little upon addition of acid or base, then the acid to base ratio varies within a narrow range, maybe 10 to 1 at one extreme and 1 to 10 at the other extreme. The last section of this chapter is called buffer solutions. Now, what are buffer solutions? They are solutions that tend to resist changes in pH upon the addition of a small amount of a strong acid or a strong base. It consists of a weak acid and its conjugate base, or it is salt. Now, examples of acid-base buffers are the following. Here, we have here acetate buffer, acetic solution of acetic acid and its salt, bicarbonate buffer, carbonic acid and bicarbonate, and the phosphate buffer consists of these 2 salts in solution. How do buffers work? Now, let's compare the changes in pH that occur on the addition of equal amounts of a strong acid or a strong base to a pure water at pH 7 and to a buffer solution at pH 7. Now, this is obvious. Now, if 1 ml of 0.1 molar HCl is added to 99 ml of pure water, the pH drops dramatically. If the same experiment is conducted with 0.1 molar NaOH instead of 0.1 molar HCl, the pH rises dramatically, as we can see in this figure here. Notice here we have the unbuffered water, and which has a pH 7 and a buffer with pH 7. We add to both of them 1 ml of 0.1 molar HCl. Now in the buffered, the pH, notice that the pH decreases by only 0.1 in the buffer, whereas it decreases to the value of 3. So delta pH is here 4, whereas delta pH here is only 0.1. So this is because of the working of the buffer. The buffer resists changes in pH upon the addition of a small amount of strong acid like HCl. Now on the other hand, if we do the same by adding 1 ml of 0.1 molar NaOH, then to the buffer pH, now we expect the pH to increase from 7 to 7.1 only, whereas in the unbuffered water it increased from 7 to 11. Again, this is a drastic change in both pHs of the unbuffered water upon the addition of the same amount to the buffer, and the buffer changes very little, or it is unaffected. Now you can do this by considering a question. Consider a solution in which this is called phosphate buffer. The concentration of the conjugate base 0.063 molar and the concentration of the weak acid 0.10 molar. Then thus the conjugate base to weak acid ratio is 0.63. Now if 1 ml of 0.1 molar HCl is added to 99 ml of the buffer, the following reaction takes place, and almost all the added H plus is used up, as you can see here. Now concentrations of the conjugate base and the acid would change, and the new concentrations can be calculated, and this is summarized in this table. Now we have, before addition of HCl, concentration of the conjugate base 0.063, of the acid 0.10 molar, and this is the contribution by water. H plus that comes from the hydrolysis of water is 1 times 10 to the minus 7 molar. Now HCl added, no reaction yet. We added this amount 1 times 10 to the minus 3 molar, and this will react with this, so it will consume 0.001 from the base, forming 0.001 from the acid. So these are the new concentrations after adding this HCl. Now we can apply the Henderson-Hasselbalch equation. Now the pKa value, the appropriate pKa value for phosphate buffer is 7.20, and we apply to Henderson equation and we see pH decreases to only 6.99. This is a negligible change. So indeed this buffer worked effectively. Now, mechanism of buffers. Buffers follow Le Chatelier's principle. Now, this principle says if a system is equilibrium at stress and is applied to a stress, if a system at equilibrium is subjected to a stress, then the equilibrium will shift in the direction that relieves the stress. Now, in our case, when H plus ion is added to the buffer, stress is added to this reaction. So to relieve the stress, this H plus will react with A minus to maintain equilibrium. And this is the added H plus are being consumed by the conjugate base. Similarly, you can say when you add OH minus will react with the acid in the opposite direction to form new acid, and the stress will also be relieved by a similar way as we saw for the acid. Now we conclude here that the phosphate buffer is suitable as a buffer near pH 7.2, and the acetate buffer is suitable as a buffer near pH 4.76. At pH values below the pKa, the acid form predominates, as we saw earlier. And at pH values above the pKa, the basic form predominates. Now, the plateau in the region in the titration curve, the plateau region here in the titration curve, as you can see, indicates that now minimum change will occur where the pH does not change rapidly and covers a pH range extending 1 pH unit on each side of the pKa. That's why, as we saw in this table here, now if the pH equals this, then the ratio of base form to acid form equals this. When they are 1 to 1, then we said pH equals pKa. If you add 1 pH unit above pKa, the ratio becomes 10 to 1. 1 pH unit below the pKa, the ratio becomes 1 to 10, and so on. This is very clear in this here. With phosphate buffer, the pKa is 7.2, and here we have the so-called buffer region. The buffer region occurs at pH equal pKa plus or minus 1. Buffer selection determined by understanding the relationship between pH and buffering capacity. Now, pH changes little in the vicinity of the inflection point of a titration curve. At the inflection point, half the amount of acid originally present has been converted to, as we saw. So when the pH is 1 pH unit higher than pKa, the ratio is the conjugate base to the acid is 10, and when it is 2 pH units higher, then the ratio is 100. As I showed you in the table, so buffer solutions can maintain a relatively constant pH value, which is met at the values at or near the pKa of the acid. So this plus or minus 2 pH units around pKa, and here plus or minus 3 pH units around pKa value. Now this curve shows us the relative abundance of the acid to conjugate base and conjugate base, and it explains this actually. At the beginning we have 0 conjugate base, and we have here 100% acid. Then with time this decreases and this increases. They meet here at the inflection point where pH equal pKa, and then this continues to rise and this continues to drop. So this figure explains this figure, and these are the relationship between the titration curve and the buffering action of phosphate buffer. Now we want to define something called the buffer capacity. Because a buffer solution with low concentrations of both the acid and base forms is said to have a low buffering capacity. A buffer that contains greater amounts of both acid and base has a higher buffering capacity. So it is a measure of the amount of acid or base that can be absorbed by a given buffer solution. So we can say that the greater the concentration of both the weak acid and its conjugate base, the greater the buffer capacity, and so on. So this is the concept. How do we make buffers in the lab? This is not required. Now let's look at this making circle of buffers. Now the exact details of how to make a buffer in the lab is not required. Here I want to show you now again, this is the titration curve, and here we have the circle of buffers. Now if you have a buffer with two components, HA and A minus, now when you add small amount of strong acid like H plus, it is consumed by the A minus. So pH will decrease a little or little. Now if you add a small amount of strong base, the base OH minus will react with the acid form to form A minus, and again the quantity of OH minus is consumed. So the pH will not increase in large amounts. So again, this is the idea of the buffer. The buffer has two components, an acid and its conjugate base, and it's able to consume any added amount of a small acid or small strong base, so that the changes are negligible. Naturally occurring buffers, as I mentioned before, we have this buffer called phosphate buffer, is the principal buffer found in our cells. Buffer system in blood is based on the dissociation of carbonic acid. Again, carbonic acid is a weak acid, and with a pKa around 6.37, and it's a good buffer, yes, inside that, because it's 1 pH unit below the blood pH, which is 7.4. Now again, CO2 can dissolve in water and water-based fluids. Dissolve CO2 then forms bicarbonic acid, which again dissociate to form the bicarbonate ion, and this is a summary of the equations. So CO2 always dissolve in water to give us the bicarbonate ion, and this conversion is catalyzed by an enzyme called carbonic anhydrase, which we will talk about towards the end of this course. So again, to summarize, the buffer system can be either in vitro or in vivo. In vitro or outside our body. Example, we said here we have this table shows us example of buffers that are used in vitro, like Tris buffer, Hippus buffer, Tis buffer, etc. Don't worry about them. And again, we have in vivo inside our living body. We saw two examples: the phosphate buffer, which is found in cells, and the bicarbonate buffer, which is found in blood. Now the terms vitins, compounds that have both positive and negative charges, considered less likely to interfere in biochemical reaction than other buffers. Now most living systems operate at pH levels close to 7. The pKa values of many functional groups, such as the carboxyl and amino groups, are well above or well below this value. So as a result, under physiological conditions, many important biomolecules exist as charged species to one extent or another. Now the practical consequences of this fact are explored in a biochemical connection on page 59 if you are interested. Go to that box. Thank you.